Pleasure to be here. We have a big audience here. I'm very excited to give this presentation. I'm going to talk about some models that are upcoming. They're currently not available, but they will be pretty soon. The plan is sometime in spring 21. So if you wait a couple more months, everything you see here today will be actually available to the public. And before I really begin, I want to acknowledge all my academic colleagues and students who were involved in this the development of various software and models that are going to be discussed here today. John Wallace, Kutai Rakchal, Leo Masone, and the students from Cal State Fullerton, Nathan, Kamiar, Ross, Carlos, and Ben. You can see their smiley faces here. They had a great time working on this research, such as well as I did. The objective here was to build up on our previous work and to basically allow three-dimensional analysis, to allow system-level analysis so we can connect walls to other elements in the building, to also enable modeling complex wall geometries and cross-sections. With the 2D models, you can really only model a planar wall, and here we wanted to do C-shaped wall, U-shaped wall, and allow multi-directional loading, and provide a variety of different modeling approaches as well. So we started with what we had, and then we built up on that and really developed three new classes. One is MVLEM 3D, which is directly coming from the two-dimensional version. The second one is the similarly SFI MVLEM 3D, which comes from, again, two-dimensional version of the SFI element. And then we added also a finite element type of a model for reinforced concrete walls that I like to call quadRC, because it's really not only for walls. You can model any type of reinforced concrete planar area element with that model. So again, there's three new classes that could be used for modeling of reinforced concrete walls that's been developed in the past few years and validated, as I will show here, and they will become available pretty soon to the public. So just quickly, how do we do this? It was a conceptually fairly simple process. So we started with a two-node element, and when we essentially extrapolate these degrees of freedom and go from the two-node element to a four-node element like this. So that's what we did to allow sort of a connectivity of the other elements and to create a four-node area element, not just the beam column element. And then to allow some out-of-plane behavior, we just added simple elastic plate. And currently in plane and out-of-plane behavior, these elements are uncoupled. But they're, the idea here is to have something that is practical and stable and pretty fast, but still allows a 3D modeling. So this is how essentially these elements work. We have these four-node MVLEM models that are for the in-plane, out-of-plane elastic plate. And when you put them together, you get this MVLEM 3D. There's an upcoming publication that's currently in review. I actually received reviews, comments today, so I'm going to respond pretty quickly. So it should be published in the next couple of months. And as soon as these papers are published, the models are going to be available as well. And we did the same thing with the shear flexion interaction MVLEM. So we converted it to the shear flexion interaction MVLEM 3D in exactly the same way. Except again, now this one is much more superior in terms of capturing that interaction between in-plane interaction between axial shear and flexural behavior, because it has this reinforced concrete panel element. So these are the two models that are based on this MVLEM formulation. And then the third model is this quadRC, where we essentially took the four-node finite element and made it work with this fixed rod angle model and added as well some elastic plate out-of-plane behavior. Again, relatively simple, stable, but has some advantages comparing to these macro models, such as the MVLEM family of the models. And again, if you pay attention, there's really three different papers here that are in review currently. And as soon as they're out, again, these models will be out as well, hopefully not too long. So then in terms of validation of these models, we found these really, really well-documented tests from Katrine Baer from Switzerland and her student that essentially tested 4 U-shaped specimens under multi-directional loading. If you were studying reinforced concrete walls, you're probably familiar with these tests. As you can see, this TUA, TUB are loaded in this sort of a spider web type of a configuration. And then TUC and TUD, they had more diagonally oriented loading protocols. But so these specimens were sort of perfect for validation of these models that were developed because they are, first of all, not planar, they are U-shaped. And secondly, they're loaded in this multiple directions and pretty complex loading patterns. So it allowed us to validate the models in all different directions. Here's how we modeled these. These conceptually, they're all modeled relatively in a similar way. So for these macro models, MVLEM and SFI MVLEM 3D, this will be one element. So we just used one element per each flange because they essentially have plane sections remain plane assumption at the top and the bottom of each element. And when it comes to this finite element model, each of these fibers essentially was modeled as one finite element. So obviously much more nodes, much more elements in the model than we're using the macro models. Here you can see the horizontal, vertical discretization that's been used in these studies. And then here you can see a typical representative strain stress curves, how these material models were calibrated and put into these elements. We also applied exactly the same loading protocol as in the test. It was sort of a challenge to figure out how to do that correctly, but after a while we managed to do it. The twisting of these walls was restrained at the top, so they were not twisting and they were moving sort of translationally in all these different directions, and we applied forces at these locations where the actuators were and controlling different displacements, and applied essentially the same type of a loading history. So here you can see one animation of one of those analyses. It looks pretty interesting seeing the wall dancing left and right like this, but it's essentially going left, right, back and forth, and there's this sweep that goes in a circle, and this will be a particularly finite element one, but we did the same type of analysis with all three different models. So the next thing we're going to look at are really first of all, I just put this slide because we were measuring time, and I just wanted to kind of point out the difference between computational efficiency of these models. Here we have MVLEM 3D and we have SFI MVLEM 3D, which is much more complex because it has this complicated panel model for reinforced concrete. So it's much more computationally demanding. So each of these specimens, this analysis that had about, say, 12,000 to 15,000 load steps, it took about 1 to 1.5 minutes with the MVLEM 3D. With the SFI model, which is much more complex, it took much, much longer, about 20 or 25 minutes. Convergence rate was pretty good, like more than 99% for both of the models. And as soon as, initially we try to converge with current tangent stiffness, and then if it doesn't work, you try to do it with initial stiffness. And as soon as you go to that algorithm with Newton with initial stiffness, your analysis time just really, really slows down. So if you actually look at the convergence rate, wherever you have, the smallest convergence rate, the time increases substantially. And this was run on laptop that I'm using actually right now, so nothing fancy, just a sort of a regular laptop computer. So just to give you some idea about, how long does it take to run this analysis. So here we have 3 different models in sort of a matrix format. So this will be results for MVLEM 3D, SFI, and the quad model. And here is the load deformation response of these walls. This is particularly TUB. And here we have east-west, north-south, and diagonal cycles. This is square root sum of squares. And just kind of looking at this from the far away, I don't really see a big difference. I mean, they all do a reasonable job in terms of predicting a load deformation response, particularly in these principal directions, east, west, north, south. It's parallel to the web or the flanges. When you start doing diagonally, and when you load these models diagonally, you can see that particularly when the flange is and web is in tension, you're overestimating capacity quite a bit. Starting with the MVLEM, maybe 50%. SFI is doing a little bit better. And then the only one that's actually kind of getting close to the test is this quad model because it's a finite element model. And then what makes me think this, the only substantial difference between these finite element models and the macro models is the plane sections remain plane assumption. So that assumption is not really a good assumption when it comes to diagonal loading, which I will show you later with some strain responses actually. But just off the bat, looking at these results, when it comes to diagonal cycles, that assumption just doesn't predict strains very well. And when you use finite element, you can actually capture that shear lag effect and nonlinear strain distribution, which gives you better capacity predictions. So we did the same thing, for all the specimens. Here's just results for TUC, which is primarily loaded in diagonal direction. And the conclusion is the same pretty much. So there's not much new here, just kind of to reinforce that conclusion from the previous slide. Then we look at some strain results above the height of these boundaries of the walls. In the test, they measure the strains at the inner and outer face of the walls. We just do the center line because that's how we model it. And strains are tough to capture in reinforced concrete, especially when it comes to this multi-directional loading. But I would say all these predictions are fairly reasonable. You can kind of see from these results how they really look like without me trying to explain them anymore. Again, nothing is totally off, but it's not perfect either, right? So in my mind, this is pretty acceptable and reasonable for strain predictions at these boundaries. Now here is the profile of the vertical strains at the base of the wall compared against the test, and the three different positions: C, which is pushing all the way like to the south, diagonally to the south, and northwest. And model is obviously the red line because its plane sections remain plane, so the strains distribution is just a straight line. And you can see that at low levels, and especially when you're loading in this primary direction, vertically or horizontally, the results are actually kind of surprisingly good. I thought, this is not going to be as good as is. But when you start loading diagonally, especially here, so this is the worst case when that 50% overestimation of the strength happens. And this is, here's the reason why, right? Because you're overestimating strains by a factor of 2 or maybe even more, right? Just because plane sections assumption can't capture this nonlinear strain distributions. So this is the MVLEM model without the one that doesn't have shear flexure coupling. When we introduce the one that does have shear flexure interaction, the results are a little bit better, but again, its plane section remain plane model, so it cannot do much better. The strains are generally lower because in this model now we have also nonlinear shear deformations. So there's more shear deformation, so that reduces the amount of flexural deformation. And that's why the flexural strains are generally lower in this one. And when it comes to the finite element model, you can see that the finite element is kind of trying to capture these nonlinear strain distributions, and it's doing a reasonable job, I would say. And that's the reason why we had better predictions of the overall capacity as well. Now, another thing that's actually also interesting, and talking about the shear flexure interaction model, and similarly for the finite element model, this is really demonstrating interaction between axial and shear response at the level of each of these panels. So if you have panels that is in compression, principally in compression, that one is going to resist more shear, right? Or versus when you have a panel that is in tension, which essentially opens the cracks in concrete and you can't really transfer a lot of shear, or in some cases very little. And that's exactly what you can see from these results, right? So let's look at this picture over here, for example. You see compression is down here. This is where all your shear stress is resisted. In this case, you push the wall diagonally downwards. All your compression is down here in this boundary. All your shear is resisted here. And similarly, pushing it this way and northwest, again, all the shear is resisted at this boundary here. I think this is important from the also not just the modeling and research side, but also engineering side, because models that we use currently in performance-based design can't do this. They all assume that shear is uniformly distributed along the length of the wall. There's no shear flexure interaction, right? So the demand we predict in, say, the core walls under the multi-directional loading might not be as accurate, and we're using those forces to design the building. So this will be sort of a better, improved way to predict actually the distribution of shear demand in the cross section of the complex cross section of a wall like this. Next thing we looked at here is amount of nonlinear shear and flexural deformation. So if you have a total deformation, you can break it down into shear and flexure, right? And here we're seeing the contribution of flexural deformations to the total displacement. And again, in some directions and in the web particularly is SFI MVLEM 3D is doing very well. In the flanges, not that well. And then we're looking at the quad wall model. It's kind of the opposite. This one is doing better in the flanges and a little bit worse in the web. But overall, they both capture nonlinear shear and flexure deformations, and still within the ballpark, I would say, in terms of these contributions to the total displacement. The next thing what we did here is looking at the cracking patterns. Here you can see a video of evolution of cracks in one of these analyses, particularly from the SFI MVLEM 3D model. You can see as the wall is being pushed left to right, the cracks, basically how they generate, and you can see their orientation as well. Which just kind of like justifies the fact that this model captures seeing these diagonal cracks, right? There's shear and flexure there as well. And then we compared those cracks with the ones that observed in the test. And we have to understand that this is a computational model, but still the overall distribution, the overall orientation of the cracks is pretty reasonably predicted, I would say. So we were able to do something like that as well. One thing that caught my eye as I was processing these videos was that all these actually the form shape look different when you look at these three different models. So you have this flexural model. First of all, just looking at how they deform, right? This one, clearly it's flexural model. It has a plastic hinge at the base and it's just kind of bending, right? Whereas the rest of it is pretty much straight. The shear flexion interaction model has the plastic hinge, but also you can see this curve that tells you there's some shear deformation going on there as well. And when you look at the finite element model, you can kind of see that, and you can also see this horizontal expansion that happens in these wall elements. So horizontal axial strains, they're also being developed there. And I just thought this is kind of an interesting, this really kind of explains conceptual difference between these three models. So in the summary for this part of the presentation, there's three new conceptually different 3D models for reinforced concrete walls. They're coming in spring 21, and they're two microscopic, one without flexural shear interaction, one with flexural shear interaction, and the one finite element based model. So I think there's really nothing else left in a way to cover. So we're expanding considerably the capabilities of modeling of reinforced concrete walls in OpenSees. And again, as I said, they will be publicly available in 21. As soon as the papers come out of review and get published, I will upload the models to official version of OpenSees.